I'm going to move into the next one here, and I said this is the one that creates a little bit of an issue for us from time to time. It's when we add just a really, really small amount. And as I go through this, I'm going to talk about this making buffer solutions. I did a little bit with the Lego demo part of it, but I'll talk about how this makes a buffer solution. But what we get here early on is what's called pre-buffering. And if I were to plot this out, what you'll see is, we'll start and we'll get a little jump here in the beginning for this titration. Then it'll kind of level off, not like what we see leveling off in terms of a strong titration. It's definitely going to climb, and then we'll get a little jump, and then it'll be kind of flat once we get to that excess strong base. Well, what happens when we're in this point right here is we're really before the point of buffering. So that's why I've added this problem in with this really, really small amount. And sometimes the mathematics gets a little bit chaotic and hectic, and I'll set it up and then I'll crunch the numbers real quick and I'll give you the answer to it. Again, not going to get hung up on what it looks like, but the approach is still the same. So we're going to start with stoichiometry first, and there's a common misconception that stoichiometry rules all get thrown out when we're working with a weak acid and a strong base. And the good news is I didn't change these numbers from the problem with the strong and the strong, so it's still going to be the equivalence point with 6.25. If you remember from the earlier problem, that was the one that ended up being the equivalence point. That's where we reach that equivalence point. Now, it's going to be a different problem when we get there, but the rules for stoichiometry are still the same. It doesn't change anything about how these things react. It just changes how we approach the calculation. So single arrow stoichiometry first. NaC2H3O2 plus HOH. And now I'm ready to do the calculations. So if I remember right from earlier, we had 0.01 liters times 0.5 molar is 0.005 moles. And that's going to be a constant throughout the initial part of this problem. And now at this point, we've added 0.05 milliliters. So that is 5 times 10 to the negative 5th liters times 0.8. And so what I get is 4 zeros and a 4. Just a really, really small amount here added. So I'm going to show that that is definitely limiting. None of that left, and I'm going to take that same 0.00004, 4 times 10 to the negative 5th, I'm going to subtract that from 0.005. And I end up with 0.00496 moles of acetic acid. But here's the thing, I also form 0.00004 moles of acetate ion. So when I'm doing my equilibrium here in a moment, when I get to that point where I start doing the equilibrium, I'm going to have that value to account for. So let's turn these into molarities. So we're going to divide both by the new volume, which is 10.05 milliliters. So 0.01005, so 0.00496 divided by that value is 0.49. We'll go a couple extra significant digits there, 4935, and then on the other side, 0.00004 divided by 0.01005. I get concentration over here of 0.0398. So this is where I really don't have enough of that common ion to get to the point of buffering. Now, what does that mean? Well, in terms of how we solve this problem, it can make a little bit of an algebraic mess for us. So I'm going to set it up real quick. I'll get it to the point of doing the quadratic formula, and then I'll go ahead and crunch the numbers. I'm not going to have you sit through the video and watch me crunch the numbers, but I'll go ahead and get it to the point where you could do quadratic formula and solve it, and then I'll pause, I'll solve it, and I'll come back on and I'll post the answer to that. So now that we've done the stoichiometry first, single arrow stoichiometry, get these values. Now, what is excess? Acetic acid. How do we address acetic acid being excess? We've got to do equilibrium. But again, we have a common ion here, 00398, no H plus, 0.004, try that again, 0.4935, 4935, down by X, so I get 0.4935 minus X, and here I get up by X to be X, and here up by X, 0.00398 plus X. Now, mathematically, when I start setting this up and I get ready to do the algebra on this, that's why this one creates a little bit of a problem as far as knowing, what we can ignore and what we cannot ignore to do this. So I get 1.8 times 10 to the negative fifth Ka equals X times 0.00398 plus X over 0.4935 minus X. Now, from a standpoint of algebra and the quadratic formula that when I go through distributing that, that's going to take a little while for me to solve. So I'm going to go ahead and set it up, and I'm going to solve it with the quadratic formula, but then I'm going to come back and I'm going to talk to you again about how significant that X is. Up here, compared to this value, it's really, really small. That X is pretty significant, but compared to 0.4935, X is pretty small. So again, algebraically, I can ignore that X. I can distribute, and I do have to still go ahead and distribute here, but I can ignore a little bit and still get a relatively close answer, but it does require some work here with the quadratic formula either way. So I'll pause for a moment and I'll post the answer to it here in just a second. Alright, so you can see what the algebra looks like here. I went ahead and did this problem and went ahead and left the X in and went ahead and did the quadratic formula. Now the good news is, from a standpoint of AP Chemistry exam, you're not going to do one at this point. There's going to be ways where you can ignore using the quadratic formula, and the problem is this X value here, it's 0.00159, so it is kind of significant in comparison to 0.00398. It's not significant here, so even though we can ignore that, we still end up having to distribute the X over that, and we still end up having to do the quadratic formula. So that's what happens when we get in that point where we're pre-buffering. AP Chemistry exam, you're not going to have to do that. I went ahead and solved it. I ended up with an X value, the root that was accepted. I believe one of the roots was negative, but the one that was the positive root was 0.00159, and that ended up being my H plus concentration. And therefore the pH was 2.799. So I'm going to go ahead and record that here. And you can see that the pH kind of did jump up a little bit. So we're in that point where we really haven't started to buffer. Now, as I said, that particular point right there, that's what's going on right here. And you can just kind of make a note. You got to be able to do problems here in the beginning, because I showed you how you could get by without the quadratic formula. You got to be able to do problems from here the rest of the way out. You're not going to be asked to do those problems right there on an AP exam just because it forces you to use the quadratic formula. Alright, so the next calculation we have here is 10 milliliters of 0.5 molar acetic acid, and we're going to add 3.125 milliliters of 0.8 molar sodium hydroxide. So again, I'm going to start with stoichiometry first. Acetic acid plus sodium hydroxide makes sodium acetate plus water, and I'm going to find my amounts of each. I've got 0.005 moles of acetic acid, and we've got 0.8 molar times 0.003125 liters, and that gives me 0.0025 moles of sodium hydroxide, 1-to-1 mole ratio. So that means the sodium hydroxide is my limiting reactant. Again, stoichiometry rules still apply. It doesn't change anything. So showing how that's all used up, none left. 0.0025 moles of acetic acid left. But we also have to take into account here the common ion. We didn't have any, and it will go up by 0.0025, leaving us with also 0.0025 moles of that common ion form. Now this is what happens when we are halfway to the equivalence point. This is a definite buffer solution where we have weak acid and the conjugate base of that weak acid, and in this case they're actually present in the same concentration. Now I can go ahead and divide those by that new total volume. That total volume is 0.013125 liters. And when I do that and I divide by that value, I end up with a 0.190 molar solution, and also over here a 0.190 molar solution. So in order to calculate the pH now, and only now, because there's excess weak acid, we're ready to do equilibrium. And so, initially we have 0.190 molar, 0.190 molar acetate from the sodium acetate. And this is again why it's a buffer solution. We've got a weak acid and its conjugate base, and these resist changes in pH. The acid would react with small amounts of base. The base would react with small amounts of acid. And really we're just shifting equilibrium. We're doing Le Chatelier's principle, and I cover that in another video on buffer solutions. So this is going to go up by x. This will go up by x, 0.190 plus x, and this one's going to decrease by x. And I'm ready to set that equal to Ka. 1.8 times 10 to the negative fifth equals x times 0.190 plus x over 0.190 minus x. Now one of the things we talk about in buffer solutions, once we get to a point on these where we're out of that pre-buffering stage and we're out in here where these are starting to buffer, mathematically they get a little bit easier because we can ignore the plus and minus x, which cleans this up. But not only that, because we are equal amounts of concentration of weak acid and its conjugate base halfway to the equivalence point, those cancel as well, so x, or H plus in this case, is the same as Ka. So the H plus concentration is actually equal to 1.8 times 10 to the negative fifth. Or we say pH, negative log of H plus, equals pKa, negative log of the Ka. So when I take the negative log of 1.8 times 10 to the negative fifth, I get 4.74 and 4.745, the pH at that point halfway to the equivalence point.